Hello, welcome to this video on Unit 1, Lesson 1 of Geometry, Point Line, Plane, and Postulates. So we're going to start by undefining or describing the three basic undefined terms in geometry. They are point, line, and plane. Space technically is not an undefined term, but point, line, and plane are undefined because they technically do not exist, and I will explain why after we describe each one. So a point is a location. It's just, normally we use a dot to represent a point, but you can use a little dot, you can use a bigger dot, you can use stars, X's, little shapes, because it just lets you know where something is. Like when you graph 2, 3 on the coordinate plane, it's just letting you know where it is. So it doesn't technically have any dimension, which is why we say it's zero dimensional right here. It has no location, or it is a location with no length, width, or depth. No size, no shape, because we use different shape to describe them. When you name a point, you do it with a capital block letter. So that is point referring to point A. We don't have to write the word point in front of it. A line is one-dimensional. It is infinite length. It goes to the right, left, forever, on and on and on. It has no width or depth. It technically doesn't exist because this line that I just drew has to have a width indicated by the writing instrument, or I could not draw it in our three-dimensional spatial universe. Usually to name a line, we will name it with 2 points. The 2 points can be anywhere on the line, and you can name it in any order. So I can call this line AB with 2 capital block letters, or line BA if I like. If there was a different point on the line, I could name it with any 2 of the 3 points I had. And you can also name a line by putting a lowercase script letter at the end of the line. Well, not the end, but along the line somewhere. So that's another way to name a line. And you don't have to put the word line in front of it because we know it's a line if you name it that way. The last one is a plane. It is two-dimensional. It's infinite length and width. You can use any plane figure, any kind of polygon, from the smallest number of sides being a triangle up to as many sides as you want. Hexagon, octagon, pentagon, decagon, doesn't matter. A parallelogram, like I've drawn here, is commonly used. It has no depth. So if you think about the closest thing we can get to a plane in our three-dimensional universe is a sheet of paper. A sheet of paper has length and width, but it also has a depth because if it didn't have a thickness, which is very, very, very thin, it could not exist in our three-dimensional universe. So planes don't technically exist, but we use them to model things. So typically when you name a plane, you name it with at least 3 letters. If you name it with 3 letters, you can do them in any order you want. So unfortunately, there's no symbol for plane, so we would call this plane ABC. Okay, or plane CAB or plane BAC. Any order of those 3 letters would work. Once you put a 4th letter, then you have to start at one point, it doesn't matter which point, and go around the figure, either clockwise or counterclockwise. So I could call this BCDA or ABCD. I could go DABC. I could go DCBA. What you can't do is make like a Z. I can't go plane BCAD because that does not encompass a plane shape. It makes the letter Z. If you name it with 4 points, that's where you have to start worrying about that. It's not possible for that to happen with 3 points. So these are just a couple of ways you could name this plane. There's lots of ways we could name it. You can put a point in the plane and name it. So I could call that plane BEA if I wanted to. And that works too. So I typically like to name a plane with 3 letters because I can just do it quickly and not worry about order. You can also name a plane with a capital cursive letter in the corner of it. So that would be planar. So when I put a capital cursive, make a lot of loopies on there, we know you mean it to be a script letter. So those are our 3 undefined terms in geometry. Every other term is based on these 3 terms in plane geometry. Space, well, you get space once you have a three-dimensional existing object. It has infinite length, width, and depth. So in order for something to exist in space, we would have to have a 3D picture. Like, for example, I could do a pyramid, and now I have a three-dimensional object because I have a plane and a point above that plane. We don't name space, because space is just the set of all points everywhere. All right, a couple of words you need to be familiar with just because they come up in words and in other discussions on postulates, theorems, and all of that. Determine. Determine means forces to exist. Contained means a group of items or an item is within another group. Okay? Um, Contained would be existing within a group. So an example of determine would be, for example, if I have 2 points, it's going to be our first postulates. That determines a unique line because I can draw a line through those 2 points. Contained would be like, for example, all the even numbers are contained within the whole numbers. I could actually use a Venn diagram for that if I wanted to. Because whole numbers, I'm going to name this the other way around. The whole numbers would be the bigger group, and the even numbers would be the group within that group. So whole numbers are like 0, 1, 2, 3, 4, 5, and so on. Even numbers are like 2, 4, 6, 8, and so on. So they are within the whole numbers. All right. Collinear. Those are points together on the same line, where they're all together on the same line. If even one point is off the line, then all the points are not collinear as a group. Non-collinear is, of course, points that are not together on the same line. So here's a picture of 3 collinear points, but the fourth point is not collinear with the other 3. Okay. Distinct means different, and so does unique. Okay, so for example, these 2 points up here, A and B, form a distinct line, which is different from every other line that I could draw anywhere else on this paper. It's a unique line that contains those 2 points. An undefined term, we already talked about that. Point, line, and plane, because they do not exist in 3-dimensional space. We just use the pictures of them to model things. And another word we will use is postulate, also called an axiom. Just depends. Axiom is more of an old school word. Postulate is more of a new school word. But they mean the same thing. They mean it's an assumption. It's something we take for granted that we do not prove. And the very most basic postulate we have, going back up to here, 2 points make a line. We're never going to prove it. We take it for granted. Yes, if you have 2 dots, you can draw a line between them. Okay, a few symbols that you can be comfortable with because I use sometimes, and you have the choice to use them or not use them. It's up to you. And, like if I said you were solving a linear system and you were to solve for X and Y, I could write it like this and save myself writing 2 characters. We're going to use that a lot when we get to logic and truth tables. Or Maybe like in algebra 1 when you were solving a quadratic and you would get the two x-intercepts and you would say, oh, well, it crosses the x-axis at 3 and 2, so x equals 2 or 3. It's a short way you can write that. Therefore is used to summarize something. You write some statements and you want to say, therefore, what I said is true. You could just write the 3 little dots instead of the word therefore. Union is when you put two groups together to create a bigger group. Sometimes they overlap, sometimes they don't. So, for example, the real numbers are the rational numbers united with the irrational numbers. So, rational is Q, union, irrational is I. You should have gone over those in pre-algebra and algebra 1. So that's when you put two groups together. Put two groups together. If they overlap, you don't list the overlaps twice in your new group. And then intersection is when you cross two groups and see what they share in common. So like, for example, in algebra 1, if you wanted to find the intersection of these two lines, line L and line M, and you found that the point 1 comma 3 is where they cross, you could say L intersect M is the point 1 comma 3. Or more simply, if you wanted to say, where do the whole numbers intersect the natural numbers, the answer would be the natural numbers, because the numbers 1, 2, 3, 4, 5, and so on are within the whole numbers, which are 0, 1, 2, 3, 4, 5, and so on. So the elements they share in common start with the answer of the number 1 and so on up the list. So those are some more symbols you should be familiar with. Now we are going to go over the existence postulates. There are two types of postulates we're going to cover: existence postulates and intersection postulates. The existence postulates are what forces something to exist. What's the minimum you need? The first one we've talked about already is that if you have 2 points, let's say C and D, they force a line to exist between them. So they determine the existence of this unique line, CD. The reverse is true. If you have a line like CD, it contains at least 2 points, C and D, and you can put other points on the line as well and use them. So these two are kind of opposites of each other. So that has to do with determining a line. Let's talk about determining a plane. To draw a plane, the smallest number of sides you can use to model a plane is a triangle, 3 sides, 3 points. So if you have 3 distinct, different, non-collinear points, not on the same line from our previous words, then that's enough to determine a plane exists because you can make a triangle. But you have to remember that triangle extends forever. Okay. Now you can have 4 non-collinear points where one of the points is not on the line with the other 4, and that works too, but you got to have at minimum 3. Other plane determining criteria, which is this one here and here and here, these will also, I'll show you how they end up 3 non-collinear points. If you have 2 distinct intersecting lines like that, that will make a plane because each line contains at least 2 distinct points. So 2 points on that line, 2 points on that line. We can see that we have at least 3 non-collinear points making a triangle, making an infinite plane. Another plane determining criteria is a line and a point not on the line, because the line we know contains at least 2 points. So we have at least 3 points, which means we have a triangle, which means we have a plane. And then the last one is parallel lines will determine a unique plane because each line contains at least 2 points. And as soon as we have 3 points not on the same line, we have a triangle, we have a plane. So all four of these ways, and this is definitely on the test, will determine a unique plane. The reverse is true. Any plane contains at least three distinct non-collinear points. So if I give you a plane, you can put as many points as you like on it, but you definitely can put at least three to name the plane. And it can be points in it, points around the edge, because remember, the edge is really not the edge. It goes on forever. And then four distinct non-coplanar points determine space. Yes, as soon as you have 3 points not in the same plane, they make, or not in the same line, they make a plane. And when you put a fourth one above it, then you get a three-dimensional object, which creates three-dimensional space. You can also do a plane and a point not on the plane, because that's the same as having 3 points that are non-coplanar. I mean, you can connect it to the fourth one if you like, but you don't have to. You have to have three-dimensional space for that. So these are our existence postulates: how to make a line exist, how to make a plane exist, and how to make three-dimensional space exist. The last set of postulates are our intersection postulates. It just says if two things intersect, or three things, what are the points they share in common? Okay, do they share just one point? Do they share so many points to make a line, or points to make a plane? So if two lines intersect, like this one and this one here, and if they're distinct, they're not the same line, like in Algebra 1 when you had infinitely many solutions. Nope. But if they intersect, they share 1 point in common. So if they're different lines and they intersect, it's definitely 1 point. If two planes intersect, like maybe this blue plane here and this red plane, like the corner of a room, like the back wall and the right wall, you can see their intersection is this line right here in the edge. So it's infinitely many points in the shape of a line. If three planes intersect, they can do so in a line or a point. Here's some pictures right here. This I will label with a 3 because this in a line. Here's the line that they all three intersect in. So that's this one. And here's 3 planes intersecting in a point. So it's that one. If I won't ever ask you to draw 3 planes intersecting in a line on a quiz or a test, because that's really hard to draw. But 3 planes intersecting in a point, this one here is hard to draw. But this one I'm going to draw for you is not hard to draw, because if you can draw a cube, oops, my pen's working wonky right now. If you think about this cube, you have the front side, the green side, you have the right side, the yellow side, and then the top side I'll make blue. And you can see all 3 of those sides are planes, and they intersect at that point right there on the corner. So that's easy to draw 3 planes intersecting in a point. So these 2 are kind of the same picture, or represent the same thing, 3 planes intersecting in a point. If a line and a plane intersect, they do so in a point or a line. Absolutely. If you draw a plane and you want to make a line intersect, you can make it intersect in one dot, like jamming a pencil through a sheet of paper, or you can put the line in the plane, in which case the line and the plane share all the points on the line in common. So they can intersect in a point or a line. Here's another picture of 3 planes intersecting in a line. You have the gray plane, the top of the box, and the left side of the box. They all intersect right here on the edge. So that's another way it could be drawn if you like. All right, let's go over 3 kinds of special lines that you need to be familiar with, which are parallel, perpendicular, and skew. You probably already know what parallel and perpendicular mean, but I'm going to review them anyway. Skew, you probably have not heard of before. So you did parallel lines in Algebra 1 when you graphed linear systems. You know parallel lines do not intersect. I'm going to add another word here, though. They are coplanar because you graph them on the same xy coordinate plane. So coplanar, non-intersecting. There are other lines that are non-intersecting, but they're not coplanar. We'll talk about those in a minute. Those are skew down here. And then parallel planes are also non-intersecting. So I'm drawing, it looks like one sheet of paper floating above another one, kind of like the ceiling and the floor. Those are parallel planes. So I'll just name, that's an example of parallel planes. You could highlight them on a cube too, if you like. Like if you made a cube here, you could highlight the top of the cube and maybe the bottom of the cube, which I need to finish drawing the cube first. And that would represent some parallel planes. All right, let's look at perpendicular things. Perpendicular lines, you learned in Algebra 1, they have opposite reciprocal slopes. Don't worry, we'll get around to that here. But they make a right angle. So perpendicular lines intersect to form a right angle, and we put that little box there to indicate it's perfectly 90-degree angle. Perpendicular planes also make a right angle. That would be easy to draw on a cube. I like to use cubes for things because most people know how to draw them. So if I'm looking at this cube here, okay, if I look at the left side, and then also I'm not going to be able to color it because I just highlighted too much. The front side, along with the left side, I can see there's a right angle in the corner between them. Okay. And then a plane perpendicular to a line is fairly easy to draw. I have my plane, I have my line going straight down through it, and I can see there's a right angle between there. Just because something looks like it's a right angle, you can't assume it's a right angle. There either has to be written information or this perpendicular mark to tell you it's a right angle. Skew lines, unlike parallel lines, which we said parallel lines are coplanar and non-intersecting, skew lines are non-coplanar and non-intersecting. In class, I used a meter stick, actually 2 meter sticks, to model what skew lines look like. And I mentioned that you might be asked to, like on an assessment, highlight a set of skew lines on a cube. So if you look at this line or this edge that's going that way, and then maybe a different one like this one, if this was in 3 dimensions, they would never intersect. Think of it like a room. The edge going up here will never intersect the edge going down here. Now, I know they would intersect actually on this paper over here, but this is flat. We're thinking in 3 dimensions. That's why they would never intersect in 3 dimensions. And then here's an example of a type of problem on your worksheet. It says draw a picture that meets these conditions. Line AB and line CD intersect at E. So here's line AB. Here's line CD. And they intersect at one point, E. Both lines are contained in a plane, which is called P. That's one of the ways. There's lots of ways you could draw that picture, but that's one of the ways you could draw it. So that is the end of this lesson on point lines and planes. I will see you for our next lesson on distance and midpoint.